Hello everybody and welcome back to another episode of this series. We are still trying to write our kernel from scratch, and currently we are trying to make our machine fire on all cores. So let's get started. Right, so before we get started, let's take a look at what things have changed. So if I go up here to memory, late init, here I've actually hooked up the slab allocator. Or rather what I call cache manager. So this cache manager here has a number of slabs of different sizes. So we go from, I believe, so let me take a look at the default config. Yeah, so we go from 4 bytes to about a page size. Anything below 4 bytes would allocate 4 bytes, and anything above a page size would trigger an error and should go through the page allocator instead. Right, so this cache manager has different caches, and every cache is a sort of slab manager. So we have a free, a partial, and a full list of slabs. And obviously, as the names indicate, they contain either free slabs, so slabs that have no items allocated off of them, or partially allocated slabs, or in case the slab is fully allocated, they go to the full list. And of course, we have some logic here to allocate and free the items from the slabs, and some less than ideal but working logic to handle inactive slabs. So for example, we don't want to have too many slabs that remain in the free list. So we have a sort of parameter here that basically says we want to have a maximum of 2 free slabs in the free list. And anything above that just gets released back. So we release the pages back to the page allocator. So safety here is still not implemented. There's absolutely no double alloc or double free checking. That's to be done soon, TM. Right, so back to main. There's also one other change that I've made. It's a small one, but it's made in preparation for what we are going to do today. That's in the CPU subsystem here. So what I did is I've created this CPU data struct, and the idea is that we are going to have one such struct per core, and it's going to contain any data that we want for said core, so that we can have an easy lookup for core-specific data without having to... and it's easy, and it should be lockless, so we can just hit our own course data without having to take a look to some shared data structure and stuff like that. So it should be fairly fast. Is the idea. Here we are going to set for every CPU, we are going to set this CPU data, or at least the address of it, in the GS segment selector. And then we are going to offset into that GS segment with the offset of the variable that we are trying to access. So for example, here ID will be in GS0. Of course, that would only work if I put this to extern, and not sure why I didn't do that, but okay. So the ID, or if we access, if we do something like ASM move like GS0, something like this should return the value, or it should put... let's give it some register or something. This should put the value of CPU ID into RAX, and we can get that. Same here goes for, here we have some ARC-specific CPU data so that we can store things depending on the architecture. And of course, obviously afterwards we might add a few other things related to scheduling and stuff like that so that we can more easily find what our core is doing. I've also added these counts and masks. So there are 3 of them, possible CPUs, present CPUs, and online CPUs. It should be fairly self-descriptive, but possible CPUs is the number of CPUs we can manage. So basically, they depend on this max CPU variable that we supply when we build our kernel. So for example, this would be 8 by default, I think. Whoops, this is not where we want to be, makefile. Yeah, so this one here would be 8 by default. So that means that the maximum number of CPUs that we can work with is 8. So that also means that if we have 16 cores on our machine, we will only be able to address 8. Present CPUs are the CPUs that we have enumerated some way or other. So basically, when we go through the ACPI APEC table and we find all the cores, we are going to mark them as present. And online CPUs are the CPUs that when we boot the cores, when we let the cores run, at some point they are going to set themselves as online, and that's how we are going to know that they are ready to accept work from the scheduler and stuff like that. So that's pretty much all there is to it. Here we have this table here, or this array, I should say, which basically has CPU data for every CPU. Here I've aligned them to a page size, but actually I should have aligned them to a cache line. I just don't yet have a way to get the cache line size for the architecture, so maybe that's something that we need to work on. Obviously, that means that when we enumerate a CPU with ACPI, we are going to call this set CPU present with the CPU ID. And when we boot the CPU, it's going to show up as online. So we are going to call this init core function here and have it call set CPU online and create the CPU data for set CPU. And that's pretty much all there is to this. So there are a few things that are going to change here, but very few. Actually, I'm not sure that this would work. At least I'm not sure that this should be an error. To do maybe just warn about this. And maybe we can set CPU present. If it's online, then why shouldn't it be present? Cool. Very nice. So with this, we can actually get to where we want it to be. So here, SMP init, this is where we left off last time. And we have created this iteration context here that basically sets this callback, and it gets stuff from the table iterator here. And yeah, so first of all, I'm getting rid of this. And then, yeah, so let me just do how do we go about this? Sure. Yeah, okay. And here we can do const message of type. So let's call this a big event. epic parsing event. Yeah, sure. This one would be args, and of course we need to define this somewhere. So I'm not sure where we are going to be putting this. Where is ACPI? ACPI should be here. So maybe we can go here. Yeah, this is not ideal. Let's call this ACPI events. This is not ideal, but we are going to live. So this one here is a public constant, called that a big parsing event, I believe, and this would be a union with some enum. Sure, why not? And here we want to have so 2 messages for now. The first one being the so hold on, I need to go to ACPI iterate table, and so hold on, where are we calling our thing here? Context.notify. Okay. So we have this LAPIC address. So this needs to change afterwards, of course, but you know what? Let me just do this. So local epic address, and this one, of course, would be AU64. Hold on a minute. What is this? Okay, very nice. Oh, I see what the problem is. My ZLS version is too old. Hold on a minute. Okay, problem solved. So this one here would be AU32, this one, and yeah, we should be okay. Cool. Now, we had another message here, which is big compatibility, ability, and this one is a Boolean. What we have? So where is the next notify here? Oh, we still haven't called any of them yet. Very nice. So let's actually do that. So this one here would be context.notify with and of course, yeah, let's hold off on this until we change the notify signature here. Right, so this one here would be so epic, sure. And what do we have here? What are the things we can have? So we have processor ID and epic ID, as well as flags. So we are going to get all of those. So this one here would be a struct. Let's just pull that out here. So epic event sure, found event, and this one here would just be a struct that has let's call it ID. Yeah, sure, ID, that's a U8. Epic ID, it's a U8 also, and flags, but flags, I think we only have a few of those. We have enabled and online capable. So enabled, bool, and online capable. Not sure what this means just yet, but I'm pretty sure it means something. So this one is epic found event. Cool. Right, so if we go back here, let's panic on this. Unhandled. Yeah, I'm not sure we want to panic on that though. Yeah, I'm not sure what to do here though. So let's just make these all errors, and yeah, okay, that should do it, I think. Right, so let's tackle this notify thing here, and of course this one here is so great that we have so where is this defined? It's defined here, and I'm guessing that now we can move it to just this. So is it defined somewhere else? No. Cool. Very nice. So this one here goes, this one stays there, this one goes. This one also goes. Very cool. Right, so now here, we can go back here, remove this, and we can do MADT, hold on a minute, MADT, parsing, event, and of course this would do local epic address, and we can set that to this. Use of undeclared identifier. ACPI events, I think, and that's in, well, first of all, let's do this, is import Falcon there, this one here. We just do this, and then I guess this one would just be ACPI events, and of course we need to go here, dupe this, and add events here, and events here. Very good. So does this work now? I think it does. Okay. Fine. So where were we? We were here. So this one is ACPI events dot. There we go. Okay. So now let me just. Whoops, not what I want to do, but okay. Let me just do this. Cool. So here we want ACPI events, MADT parsing event, and here big compatibility is and I forgot. True, I guess. Yeah, that looks okay. Actually, we could have. I'm not sure we can do this, but if we can, then that's great. Because we only need to see this to know it's compatible. We don't need to set a value for it. Cool. So now here, ACPI events, obviously, MADT parsing event. And this here is epic. And this here is ID. It's not how we do it. ID. Or maybe it is. ID is where. Okay, so it's processor local epic dot processor ID UID, and then we have epic ID, which is processor local epic dot epic ID, obviously, and here enabled. Whoops, enabled is processor local APIC dot flags dot enabled, and online capable is processor local APIC dot flags dot online capable. I'm just going to do this for so we can read this, and I'm just going to add this one here also. Cool. Very nice. We'll get back to these, if we need to, but for now, should be okay. All right, so this one here is APIC or ACPI events dot. So we call that MADT, and of course here we need to const ACPI events is one second. Yeah, so this one be in Falcon and ACPI events. There we go. And let's do received ACPI or MADT parsing event, and this should work. Hopefully, this should give us the tag name for our enum, and if it doesn't work, we'll know why. Expect U16 found U size in CPU 51. So that's U size, of course, and that's U16. So just going to endcast that. Sure. I'm going to do the same here. Oops. Endcast. Okay. Okay, it looks like it's happy. This looks also happy. And do we have... Yeah, we do have our events here. So received MADT present events, local APIC with our address, big compatibility with the void that worked. Okay, great. And here we find APIC 0 with APIC ID 0 enabled, online capable false. And they're all pretty good. Yeah, so they're all pretty good. So now let's just want to take one look at the ACPI spec. If we can get to that. And I want to take a look especially at so where are the tables? Where are the tables? There we go. I want to see what this where is it? This here, online capable means. Okay, so basically this should be 0. It's fine. System hardware supports enabling this processor during OS runtime. Okay. Okay, so basically we just ignore this then. Very good. You don't need to tell me more than that. Okay, so let's go back here. We have parsed all of these things now. We are just going to change our message there with some actual dispatch. So switch an on message. We are going to get are we not getting any? So local APIC address, of course. So local APIC address. This here we get local APIC address. Sure. And with that we call set local APIC I'm not sure we need to do that. We need to do local. So we don't have self here. We have a const. So let's get a self here. This with immediate iteration context, of course. So this one would be a pointer cast. Yeah, sure. Let's align cast that also. And let's call it pointer. Let's call it, whoops. Come on. Right, so if this goes here, we can do self dot local, let's call it lapic address is local lapic address. Okay, so now we can do, what's the next one? Big compatibility we are just going to ignore. So big compatibility. Let's not ignore it. Let's say big compatibility. This is hard to type. Is true. Okay. And of course the other one is epic, I believe, and this one self dot. So hold on, how do we go about this then? I guess here we don't really need to keep any info here. What we can do is actually just CPU. Let's import const CPU. Whoops, is import CPU dot. Okay, I can do this. CPU.zeg. And we can go down here and we can do CPU.set CPU present, and we can set, and of course here we need to capture that as epic. Whoops. Here we can do epic.id. Probably should do epic.epic ID here. Yeah, so hold on, let me think for a bit. So CPU present, we set the epic ID. And I should probably do something like epic ID is yeah, sure. Hold on. I'm just riffing this off from the top of my head. Not sure if this is a good idea or not, but you know what? We'll be fine. Okay, so this one here, we should also set let's call this epic base. Let's call it lapic address. That's fine. Self dot. What did I call that? Lapic address. Sure. Okay. So now here we need to create a few things. So ID is AU32. Is it AU32? Let's go for a U8 for now. Okay. Or wait, hold on. What am I doing here? Lapic address. This one here would be a U32. Yeah, that was okay. Pick compatibility is a boolean that defaults to false, and I'm pretty sure that's all there is to it. Okay. So that's marked as Oh, I see it. I see it. Pretty sure that this now needs to be not const. And I'm pretty sure that this now needs to be a variable thing. What is the misinstruct? Okay, that's fine. I can just set it to this. Enable to evaluate comp time expression. Call to function with comp time return type is evaluated at comp time. What is going on here? Not sure why he wants this to be comp time though. Does this expect this to be comp time? I don't think so. Oh, I see. I see what the problem is. Well, no, not really. I don't see it. Maybe this one here. Maybe this should do the trick somehow. No. Wait, is it the same error still? Yeah, it is. Enable to resolve comp time value. What are you on about? Okay, so now they want this to be a variable. And now this is okay. So this pointer is a any opaque, and this one here has the correct signature, I think. So any opaque arguments any type. That's exactly what we have here. So I'm not sure what the problem is with this. Why does he want this to be comp time? Oh, is it? Oh, I see. It's because of the any type arguments, I think. This is okay, fine. So I guess this can go there. Does that solve the problem? It does not. Yeah, sure, fine. Yeah, this will not work. This will not work this way. Fine. So this one stays const. This here goes. And we set here set local epic address which should take some u32 turns void, and this does, and of course we should have so epic address is address. Sure, okay, fine. So variable epic address u32 is undefined. That's okay. And here we go and we do set local epic address with lay. Fine. For pick compatibility Boolean and it's undefined. Let's say false. Set pick compatible. And this does pick compatibility. Whoops. Pick compatibility is true. And then of course here, yeah, sure. Set CPU. Sure, let's call it set CPU present. And it's going to take a CPU ID in the form of a U8, and it's going to take epic ID. The problem is that now this is very, very platform specific. I'm not sure we have epic IDs on ARM, for example. So yeah, I'm not sure about this, but okay, let's move forward, I guess. And that's pretty much all we need. This does void, and this does CPU. This does CPU dot set CPU present of oops, epic. Wait, hold on a minute. Oh, that's epic.id, so that's CPU ID. And then here we are going to pass it some sort of platform specific thing. Blob here, which should be, this one would be epic ID. And then here we should pass it epic address, sure, is epic address. Hopefully that does the trick. So let's first start with this. So set pick compatible, and then here's set CPU present that takes what did we call that? Epic dot ID and epic dot epic ID. Okay, so now we can get rid of this. We don't need this anymore. This can go back to being const. This also can go back to being const, and these two can go back to being const also. All right, fine. So const, that does that does this. That should be happy. That should be. It's not happy. X with one argument. Okay, that's fine. So SMP. Yeah, SMP, that's fine. So if we go here to set CPU present, we might want to do CPU identification. No. So thinking, I guess arg CPU ID identification, which should be something like arg CPU present so let's call this ID data. Fine. And of course, we need to go here. We need to go and do identification data something struct. So in our case here for x64, we want epic ID, which should be a U8 or something, and we want epic address, which is a U32. Okay, actually, let's go back here. Identification data. Okay, that's fine. Yeah, I'm just going to do this here. Does this work? It does. Cool. So now let's do this here. Okay. So we do have the ID, and here we have we init that with ID and with ID data, and here we can go ahead and so this one is CPU data that takes in ID and identification data. It's fine. ID data is that. Cool. Very nice. So now we should be able to do epic base address is U32, and we should also be able to do epic ID is U32. Let's call it CPU ID for BreFT. So this one here we don't really need. And what we need is to actually do this. So epic base address is id data.epic address. Whoops. And this epic ID is id data.epic ID. Hopefully this works. So let's go back here. This should be okay. And this should be also okay. There's only one thing I want to add. So I'm thinking here. Yeah, it should be in main. Where is main? Main. There we go. So here I call this here, but it should actually be called somewhere down here. Yeah, that's fine. Let's try to build this now. Okay, so still two more errors. External structs cannot contain fields of type CPU data. Okay, fine. I believe that's because the CPU data here needs to be also an external struct. And so does this one? No, I don't think so. Okay, that's fixed. Expected 2 arguments found 1. Okay, so that's in CPU here, and I think that's somewhere here. Fine. This one here can be optional. Sure. We can do this. Fine. Fine. And no, actually, hold on. Let's not do that. Let's not do that. Let's actually leave that be. Let's make these optional. And let's actually init them with some default value. Does that work? Yeah, I'm not sure that works though. But now this should definitely be an error because, yeah, okay, that's fine actually. Yeah, I'm just going to take back everything that we did here. That's okay, and this one should just be an error. I think we should not be trying to do that. So return error. CPU not present. Not present. Okay, and I guess we can just get rid of these now. This time it should just build, hopefully. Okay. And let's see. Okay, so we so we have no errors. That's good news. Well, hold on a minute. We have errors about the IO apex that we haven't yet handled, but that's okay, I think, for now, at least. That's fine. So now let's do something here. Let's go to main, so kernel main, and we are going to just after this try to print. So let's go log info present CPUs, and yeah, let's just give it that for now. So present CPUs count. Yeah, the count is good, and then we probably want to have the present CPUs mask also in there. So let's do this and do mask. Sure. So do we have some? No, that should be fine. I should just figure it out. Cool. Oh, right. So let's see here. So we have 8 CPUs on, and the mask is 255. I believe that's okay. Yeah. Because we have 8 bits and all the bits are on, so that's okay. Let's actually try to make this a bit harder on ourselves by just having fewer CPUs. So let's go for 4 here, and we'll see if that affects the mask somehow. Yep. So I think we are doing okay. So 4 CPUs. The mask is 15. So if I open my trusty calculator here and I just put in 4 bits in the mask, and it gives us 15. That's okay. Very good. Now we are actually done with this part. So let me just also for now print online CPUs with the mask. That's fine. Actually, let's do present goes online. It should work. Whoops. No. Hold on a minute. Let that build first. And of course, here we can go for And yeah, so we have one online CPU, which is the BSP, Bootstrap CPU, that we are currently running on. The others are still waiting for a signal from us to actually run. So that's what I want to discuss now. So let's get away from the code for a second and go to my second favorite thing to do in the world. At least that's what I've been trying to convince myself of, which is reading this documentation here. Right, and I think if I remember correctly, it should be under chapter 10, and there should be some sort of so it should be, no, that's not it. Very nice. So I don't remember. Oh, it's here and it should be here. Cool. Very nice. So in chapter 10.4.4.1 and 10.4.4.2, we have what Intel thinks should be the typical Bootstrap processor initialization sequence and the typical application processor initialization sequence. So let's go through these and try to think about how we want this to be implemented on our kernel. So there are things that we've already done, but there are things we are going to need to do to make this work. So initialize memory, that's fine. This, we don't do that. MTTRs or MTRRs, we did not use. Enable cache, that also goes with the MTRR. So execute CPU ID, of course, we are going to check for genuine Intel, of course. That's definitely something we want to do. This here, we don't really care about. Load startup code for the AP. Okay, that's a mouthful, but so basically what they say here is that we need a page in the lower 1 meg of memory, which would serve as a trampoline, so that we basically tell the AP, can you start executing from this code here? And that code, that startup code, should basically bring the AP from read mode to and make it catch up to the BSP in long mode. So it should do everything we did to boot our BSP from read mode, set up all the registers, go to protect mode, set up the paging, and then go to long mode, and then execute a jump to our kernel code. So here, switch to protected mode and ensure that APIC address blah blah blah. That's fine. We probably don't have this, so strong and cacheable memory type. At least the APIC address is not mapped there yet. We can fix that by remapping that address to some pages with paging disabled or caching disabled and write-through disabled. So this one here, we get the APIC ID. That's fine. We did it from ACPI. There are a number of ways to do that. So convert the base address of the 4 kilopage page into an 8-bit vector. So this basically is what we discussed before. So if we have this page here, we just take, we shift it left by 12, and we take the two bytes, or rather, yeah, the byte that's in here. So that vector would be BD in this case. We enable the APIC because there's a setup to do for the APIC to be enabled. And then we set some sort of LVT. Yeah, I'm not sure what this is, needs research. And then here we broadcast the signal that will actually tell the APs to start working. So this one here is init CP. And I guess IPI is inter-processor interrupt. Here we do this sequence here, and we should have a table here that tells us how to do that. So when the processor count is known, we do this. So ICR low is just an address we write our messages to. They put that into ESI, and here they send this message here. I guess this is an init IPI, and they broadcast that. They send it to the other CPUs. Then here they say that we should have some timing thing to wait for 10 milliseconds. And then here they send the CP IPI with the XX replaced with the vector that we for the trampoline page, basically. And they send that again through that ESI address here, ICR low. And then here we should wait for 200 milliseconds and check that the count variable has reached the expected number of processes that we want to reach. So basically we want to check that all line CPU count reaches present CPU count, basically. And then here we broadcast the same value again to all APs. And then we do this again. So until the 200 milliseconds expire. And then we should go to step 16. Right, so this means that now, let's go here. So SMP init, we should have something like, so the plan would be, lplan would be, so one, identify CPU count, that's done. Two would be, so create a trampoline page. That's not done yet. Three would be copy. Actually, this one is done. We already have a trampoline page. We have used it for our BSP's setup from the BIOS. So that's already from the UEFI bootloader. So that's already done. So here what we need to do is copy the startup code to the trampoline. And of course, here there's a simple step, which is 2.5, obviously, which is write the startup code. This is not hard at all. It will not take us a few weeks to do. Don't worry about it. So what we need to do here is we basically need to write a BIOS bootloader. Or maybe I should not a bootloader, just a bootloader, a small bootloader that basically does takes the core from real mode to long mode as fast as possible. As fast as possible? Yeah, okay. Right, and then when we get to long mode, we need to jump to have a special path in our kernel entry point for APs. So basically here, if I go to kernel main, sure. Here we come through this. We go through the setup for our stack, and we then go call in kernel main. We want here to identify that we are we an AP? Set up the AP stack. Jump to AP specific code. Yeah, startup code. Startup code. That should be okay. Right, so that's pretty much what we need to do. So a few things, obviously. The plan looks solid. So that's what we are going to start working on next time. Well, that's pretty much it for this one. If you've liked this type of content, please hit like and subscribe. We are getting to the thick of it, so tell a friend. I'll see you and your friend next time. Fucking out.